Our next lesson is on 5.3, formal definition of antiderivative and indefinite integral. So this is pretty straightforward. We've already worked with antiderivatives. Basically what they do is they undo derivatives. An indefinite integral is just an antiderivative. So we'll start with that. Eventually we'll cover definite integrals, which you'll see why they're different. But right now we're doing indefinite integrals, which are basically just antiderivatives. So it's a function whose derivative is given. And your goal is to take that derivative and antiderive it, okay? So the fact that an indefinite integral is an antiderivative, if you're given a function whose derivative is given, then your goal is to get back to that original function. So you're going to see, so for example, this is what they look like. They've got an integral sign. They've got some kind of function happening. And then they've got that differential dx. Okay, so this whole thing is an integral. This one's actually an indefinite. When we get to definite integrals, you'll have x values here that'll kind of bind the area that we're talking about within the function. Okay, this inside part here, this is your integrand. This is your integral sign, if you need to label that. And then you have your differential, which we learned about in our last lesson. All right, so an actual indefinite integral, the actual definition. Looks like this. The function g of x is equal to the integral of some other function f of x dx if and only if, basically if you took the derivative of g, then you'd get back to the original f. So if I take the derivative, or g prime of x, will basically give me the original function. So what that's saying is that derivatives and antiderivatives undo each other, or derivatives and indefinite integrals undo each other. So we have some properties here. Oops, sorry about that. So the first one is a constant times a function, which we had that for derivatives as well. That might be a little bit confusing because I like to refer to the constant that's being multiplied to a function as basically the coefficient. And whenever we took the derivative and there was a coefficient of a function, we basically just left the coefficient there, right? And the same thing's going to happen with antiderivatives or with integrals. So if you take the integral of some constant or some coefficient being multiplied to some function, then what you're going to be left with, that constant doesn't change at all, just like it didn't change when we took the derivative, okay? So that constant just comes out, you leave it alone, and then you do the antiderivative on the rest of the integral. Okay, so k is your constant. Okay, another property, integral of a sum So again, this is treated just like when we were doing our derivatives. So if you have, let's say, two functions being added together, f of x plus g of x, and you're taking the integral. So the integral sign, if you, right, by definition, the integral is always going to have your integral sign and your differential. Okay. So if I wanted to take, well, first of all, let's just pretend that I had that and I wanted to take the derivative of that. Well, I would just take the derivative of f of x and then add to it the derivative of g of x, right? Same thing with integrals. I'm just going to basically take the integral of f of x dx, and then I'm going to add to it the integral of g of x dx. Right, and the dx is there because that's part of the derivative, right? That's that denominator of the derivative. And so when we undo this, the dx basically moves back over to the other side and gets undone. Okay, how about powers? So integral of a power. Okay, so if I take the integral of, for example, maybe u to the n du, because it was u was my input, right? So I'm taking the derivative with respect to u. Okay, so when I do the antiderivative, okay, so let's think about the power rule. When we did the derivative for power rule, so let's just pretend I'm taking the derivative of that, right? I'd bring the n down, and then I'd subtract 1 from n. Okay, well, the antiderivative is opposite this, and you guys have already explored this. Basically, I'm going to leave the u here. I'm going to add, instead of subtracting 1 from my power, I now add 1, because that's the opposite of what we did before. And that also means, because, right, I would have to bring this down if I want to take the derivative of it. So that means that I need to have something that would basically reduce that out when I bring it down. Okay, so I'm going to divide out what I would normally bring down, which is n plus 1. And then let's not forget that there's always going to be some constant left there that at some point became a 0. Or if it wasn't there, it's still 0. Okay? And don't worry, I'll do many examples. But you guys have already experimented with this. Okay, and we have 2 more. The integral of e to the x. So this is number 4. All right, so if I want to take the integral or the antiderivative of e to the x dx, well, think about it. How did I take the derivative of this? I just left it the same, right? So the integral of it's going to be the same, or the antiderivative. And remember, there might be a constant out there, so we'll leave the plus c. Okay, and then let's do one more. So how about base b? If I have a base b exponential. So that was like, for example, when I did, I'm just going to go off to the side here. If I took the derivative of, let's say, I don't know, derivative with respect to x of 2 to the x. And then what I would do is I would say, well, this is really 2 to the x ln of 2, right? Okay, so when I'm doing the antiderivative of this, I need to work backwards. So I'm going to end up dividing out that ln of the base, okay? All right, so, right, because if I divide out that ln of the base, I get right back to what I started with. So your base b exponential basically looks like this. If I take the integral of b to the x dx, then that means I'm going to have my base, b to the x, and I'm going to divide out that ln of the base. And then always add, there may have been a constant. So we always keep that plus c. So I'll do a couple of examples with you. So let's do a couple of examples. Let's start with the integral of the quantity 7x plus 4 raised to the 9th dx. Okay. So, first of all, this is a power rule, right? So I need to think about the fact that when I originally took the derivative, there had been some power here. Now, what had that power been? That power had to be one more, right? So I know that I'm going to still have my base. I'm going to add 1 to that. And that means that originally when I took the derivative, I brought the 10 down, right? So, but I don't see a 10 here anywhere. So I also need to undo that 10 that I would bring down. So you kind of have to be thinking both ways. You have to be thinking, all right, I need the antiderivative, and let me go back here and let me take the derivative. So you need to be thinking forwards and backwards while you do this. Okay? Another thing that would have happened, okay, so let's say, for example, let's just stick with this piece right here for now, okay? So if I had taken the derivative of this, just this piece right here, so I'm just going to kind of come up here and do that, okay? The derivative of this then would be, well, if I bring that 10 down, I'm just going to have 10 over 10 times 7x plus 4 to the 9th. And then I would have to chain rule it, right? So then I would have had to multiply by 7. Okay, well, the problem is, do I see a 7 here either? I don't see a 7 happening here. So I also need to get rid of that 7. So I would also have to divide out that 7. So what I used to multiply by and chain rule, now I chain rule by dividing it out. And then there's probably a constant there, so we're going to do a plus c. Okay, so so this is me, taking the derivative of this thing. Okay, so derivative with respect to x. Just put a little note there so later on you don't get confused. Okay, so you'll see that I do this a lot. I go back and forth. I say, okay, what do I think the antiderivative is? Okay, let me take the derivative and see if I get back to this integral. Okay, I'm going to simplify this. So really I'd have 1 over 70 times quantity 7x plus 4 over 10 plus c. So if I wanted to check this, what I could then do is I could take the derivative, right? And if I take the derivative of this, again, I'm going to bring down that 10. I'm going to end up with, 10 over 70 times this to the 9th. Then I'm going to multiply that by the 7, which is then going to get rid of this 70, and the 10. So it all ends up going right back to what I've got there. Okay, well, let's do one more example. So that was example, we'll call that example A. And how about we do one more? Pretty simple one. 5 to the x dx. All right, so base b function. So, I have to think to myself, hey, okay, this is a base b function. So originally, there was something that had an ln of 5. Okay, and I have to undo that because I don't see an ln of 5 here. Okay, so what I'm going to do is I'm just going to write, and really you can just follow this, but you have to think, there was an ln there, I got to divide it out. Okay, so we're going to have 5 to the x over the ln of 5 plus a constant, because there was a constant somewhere. Okay, and if you don't believe me, then you can go back and you can now do the derivative of this. The derivative with respect to x. Let's try that. So let me first rewrite this, because you need to realize that ln of 5 does not have a variable in it. So it's really just a constant or a coefficient, right? So really, before I do that, before I take the derivative, let's not take the derivative yet. Before I take the derivative, I'm going to write this as, it's really 1 over ln of 5 times 5 to the x. Okay, so now I'm going to take the derivative of that. So I can just write derivative with respect to x of that. Okay, so thinking about that, well, this coefficient or constant will stay exactly the same. Okay, and then I take the derivative of 5 to the x, so that's 5 to the x, ln of 5. Okay, so when I take the derivative, look what happens to the ln of 5s, and I'm just left with 5x, which is exactly what I'm taking the integral of. So I'm trying to get back to that original function, which happened to be this. And I don't know the constant yet. Believe me, you'll be able to figure out what the constants are at some point, but we're not going to do that yet. Right now, we're just going to really master the art of finding these indefinite integrals and kind of thinking backwards about derivatives.